Good day, students. Welcome to math.serve.com. In this clip, we're going to be going over problems 11 to 15 of the AP Calculus 012 multiple choice questions. Alright, question 11 reads, let f be the function defined by f of x equals the square root of the absolute value of x minus 2 for all x. Which of the following statements is true? So if you take a look at the options that we have here, it's asking about continuity and differentiability at 2, differentiability at 2, discontinuity at 2, existence of a limit at 2, and the vertical asymptote at 2. So the focus is on what is happening with this function around 2. So a real quick tip to keep in mind is sometimes in an AP exam you'll be given a strange function to deal with, a function that you might not readily know what the graph looks like. In cases like that, what you do is you quickly generate a table of values and a snapshot of the function around the relevant areas. Okay. So in this situation, we're focusing our attention at 2. So what we're going to do is graph this function around 1, 2, and 3. Okay, so those points should give us a general idea as to what's happening to the function around the relevant values. So we're going to sketch around so the reason why we're focusing on 2 is that's the argument of your absolute value function. Okay, we're looking for where the break happens. So when you set the argument of your absolute value function to 0 and solve, you'll see where the break happens. So the break happens at 2. Alright, so what we're going to do is generate a table of values, and then that will help us to draw the graph. Okay. So input output table, remember we have 2 minutes roughly for each question, so you want to do this really fast. Okay, so we're going to do 1, 2, and 3. So we're plugging it into the function square root of the absolute value of x minus 2. Alrighty, so when I plug 1 into this function, I'm going to have the square root of the absolute value of 1 minus 2, which is going to be the square root of the absolute value of negative 1, which is going to be the square root of 1, which is 1. For 2, what's going to happen? We're going to input 2 into the strange function here. Square root of the absolute value, we'll have the square root of 2 minus 2. Square root of the absolute value of 2 minus 2, which is the square root of 0, and that yields 0. Now for the last input output, we have 3. So we're just trying to give ourselves a visual as to what is happening around 2. Okay, so at 3, plug that in. We'll have the square root of the absolute value of 3 minus 2, which is going to be the square root of the absolute value of 1, which is the square root of 1, and that's 1. Okay. Alright, let's go ahead and sketch the graph. When we see the graph, it's going to be much easier for us to answer the question. Okay, so what do we have? We have, let's call this 1, 2, 3. So we have 1, 1, 1, 1 right here, 2, 0, and 3, 1. Now if you plot this graph in your computer, you'll notice that there's a curve to it. So this is exactly how the function looks like. It curves a little bit like that. Now whether you have the curve or not, just having these points is sufficient for you to answer the question. Okay, so remember, this problem you are not allowed to use a calculator, so this is a non-calculator problem, so that's why we're using a table of values to sketch our graph. Okay, now let's go over the options. Remember, we're looking for which statement is true. Option letter A, f is continuous but not differentiable at A. Okay, so there are two things we're looking at there, continuity and non-differentiability. Let's deal with continuity first. So for part A, for continuity, we're going to look at the left-hand limit, the right-hand limit, and the value of the function. Okay, so let's do the left-hand limit first. What's the limit as x approaches 2 from the left of this function? So we're looking at the x value, the y value that you're approaching, and that's 0. And then from the right, limit as x approaches 2 from the right of the function. So as you're approaching 2 on the graph, what y value are you approaching? What's the y coordinate of the point that you're approaching? That's 0 also. So we have the right hand limit, left hand limit. They're the same, which means the limit exists, but that does not mean it's continuous. We have to evaluate the function at 2 to make sure they all match up. F of 2 is 0. So what does this tell us? Since the left hand limit is equal to the right hand limit, and that is equal to the value of the function, that automatically implies that f is continuous at 2. Okay? Alright, now how about differentiability? If you look at this graph right here, you have, if you draw it correctly, it's a cusp, but if you just draw the points and follow the general trend, it will look like a corner, but it doesn't really matter. The bottom line is that the function is not smooth at 2. Okay? If you have a situation where a function is not smooth, the function is not differentiable there. Okay, so we're going to say that since f is not smooth at x equals 2, then that follows that f is not differentiable there at x equals 2. Okay? So what does that tell us? F is continuous, yes, but not differentiable, yes. So both components hold. Statement number 1 is true. So this is the correct answer. Okay, option 1 is true. Okay, let's just go over the other options just to help you see why they're false. So let's take a look at option B just to make sure we understand this completely. It says f is differentiable at x equals 2. Now, is that true or false? It's clearly false because f is not smooth at 2. Okay, we talked about that earlier, so let's write that down. Since f is not smooth at x equals 2, that automatically follows that f is not differentiable there. Okay, we have a cusp right here. Okay, option C, it says f is not continuous at x equals 2. So we're looking at continuity. Now, how do you know if a function is continuous? We talked about that in part A. So we look at the left-hand limit, the right-hand limit, and the value of the function. If they're all the same, then the function is continuous. So what does we conclude or arrive at part A? We had the left-hand limit was equal to the right-hand limit. They were both 2, and they were also equal to the value of the function. Okay, so what does this mean? This means that f is continuous at 2. Okay, so this statement that's here, that f is not continuous, is false. So B is false, C is false. Now let's take a look at option D. Option D says that the limit does not exist at x equals 2. Is that the case? So for the existence of the limit, what do we have to show? We just have to show that the right and left hand limits are equal. Okay, so since the left hand limit and the is equal to the right hand limit, they're both equal to 0. What does that mean? This automatically means that the double-sided limit, written as the limit as x approaches 2 of f of x, is in fact equal to 0. Okay? So that indicates that the original statement that the limit at of the function as x approaches 2 is not 0 is false. Last one, option E. It says x equals 2 is a vertical asymptote of the graph of f. Now, what tells you that you have a vertical asymptote on a graph? You have a vertical asymptote on a graph when you have an infinite discontinuity. Either double-sided infinite discontinuity or one-sided. Okay, that's sufficient to conclude that you have an infinite discontinuity. If a function is continuous at a point, can it have a vertical asymptote? It's the same question as asking that if a function is continuous at a point, does it have an infinite discontinuity? It makes no sense. If a function is continuous, it has no discontinuities whatsoever. Jump, removable, oscillating, infinite. None of them are applicable. Okay? We already established in part C and A that the function is continuous. So since f is continuous at x equals 2, there are no discontinuities. One of which, what is one of the types of discontinuities that indicates the existence of a vertical asymptote? It's the infinite discontinuity. Okay, there are no discontinuities, one of which is infinite. And an infinite discontinuity just indicates that you have a vertical asymptote at that point. We don't have any vertical asymptotes on this graph. Okay, so that's why option letter E is false. The only true statement is option letter A. Alrighty, let's take a look at question number 12. It says using the U substitution, U equals the square root of x, the integral from 1 to 4 of e to the rad x over rad x dx is equal to which of the following? So the integration technique that we're going to be using for this problem is the U-substitution integration technique, okay? Alright, so we already told that U is equal to rad x. So we have to rewrite this function in a way that we have the composite function and the derivative of the inner of the composite function, dx. Okay, so the original problem is the integral from 1 to 4 of e to the rad x over rad x dx. Now, it's good to write it in a way that's easy to distinguish between the composite and the other functions, so your U substitution will be clean. Okay, so check this out. I'll write this as an integral from 1 to 4. I'm going to put the composite function first. Okay, so that will be f of u, and then the multiple of the derivative of u is going to be 1 over rad x dx. Okay, so I'm going to try to get this substituted and then this substituted as a package. Alright, so we have two parts. Now, a caution when you're integrating finding definite integrals using U substitution. Do not forget to change the limits. The limits do change. So 1, 4, when you're using U sub, don't forget to change that. Okay? If you look at the distractors in this question, you will notice that there are two traps there to catch people who forget to change the limits. See that there is there for a reason, because students forget. Alright, so don't fall into that trap. Okay, now to do the U substitution, we need du to take care of that piece. We already know what u is, rad x. And then we also have to alter our limits of integration. Okay, so let's split it up into two parts. Let's find du first. So we have u equals rad x. This is what we're going to use to find du. So we're going to differentiate both sides. We have du. 1 du equals 1 over 2 rad x dx. You can write this as du dx equals 1 over 2 rad x, and then multiply both sides by dx. You end up with the same equation here. Alright, so now let's compare this portion of our integrand with this portion right here. What do you notice? We have an annoyance. We have this 2 here that's not present here, so we have to fix that. Alright, the right side has to match with 1 over root x dx perfectly in order for us to make a clean substitution. So what we're going to do is get rid of that 2 in the denominator by multiplying by 2. So multiply both sides by 2. So we have 2 du is equal to 1 over root x dx, and that's exactly what we want. We have a perfect match. Okay, so we know how to fix this portion. Now let's talk about the limits for a second, okay? What are our new limits of integration going to be? Let's start with the upper limit. X equals 4 is the upper limit with the original variable x. With u, we know that u is rad x. Let's refresh our memory here. U is rad x. Okay, so that tells us that u is going to be the square root of 4, which is 2, our upper limit. Now for the lower limit of integration, x is 1, so that follows that u is going to be the square root of 1, which is just 1. Okay? Alright, so we are now ready to write down our new integral using U-substitution. Alright, so the original integral is the integral from 1 to 4 of e to the root x dx, times 1 over root x dx. That's the original problem. So using the U-substitution, it now becomes the integral from lower limit unchanged, upper limit is 2, e to the instead of root x, that becomes u. Remember, u is rad x. And then 1 over root x dx, see that right there, becomes 2 du times 2 du. Okay, so that goes our new integral using just u's. So let's make it look pretty, okay? So this 2 can be factored out. So we have 2 times the integral from 1 to 2 of e to the u du. Correct answer for number 12 is option letter C. Okay, let's take a look at question number 13. It reads the function f is defined by f of x equals 2 for x less than 3 and x minus 1 for x greater than or equal to 3. What is the value of the integral from 1 to 5 of f of x dx? Alright, so something you want to note concerning integrating absolute value. Integrating piecewise defined functions, one of which is absolute value function. Whenever you're integrating piecewise functions, you always want to break up your integral along the breakpoint of that piecewise defined function. Okay, so in this case, what is our break? Where does a function break at is a question. So we have two functions here. We have 2 for x less than 3, and we have x minus 1 for x greater than or equal to 3. Okay, so this clearly shows us that the break happens at 3. Okay, so it breaks at 3. So if we have the break at 3, that means our integral from 1 to 5 has to break at 3. So let me give you a visual as to what our limits of integration are going to be, okay? So let's say we're going from 1, that's the lower limit, to 5. And then 3 is dead in the center. From 1 to 3, we're looking at the first interval, okay? Let's call that I1. So for I1, the function that's active is 2. F of x equals 2. For the second interval, I2, from 3 to 5, the function that's active is x minus 1. So what does this setup tell us? It tells us that the integral, the definite integral from 1 to 5 of f of x dx has to be broken along the breakpoint. Okay, so that's where the break is. The break is at 3. So it has to be the integral from 1 to 3 of the first function, which is 2, dx, plus the integral from the second portion, 3 to 5, of the other function, x minus 1, dx. Okay, so just evaluate these two integrals independently, and that will give us our answer. Okay, alright, let's do it. Alright, so let's integrate the first one. Antiderivative of 2 is just 2x using the power rule. So we're going to evaluate that from 1 to 3. Okay, and then we go to the next integral. Now if we integrate x minus 1 using the power rule, and then we do term by term integration, here the antiderivative of x is x squared over 2, and the antiderivative of 1 is just 1x. Okay, so we can write that as x. We're evaluating this antiderivative from 3 to 5. Okay, so we're going to apply FTC part 1 in simplifying these two integrals here that we've already evaluated. Now let's do the first one. So for the first one, we just plug in 3. So we have 2 times 3 minus plug in 1, 2 times 1. Or you could factor out a 2 and then just plug in 3, 3 minus 1, same thing. Alright, plus over here we plug in 5 first, of course. So we have 5 squared over 2 minus 5. Now this is where you want to be extremely careful when you're evaluating integrals using FTC1 and you have a minus. Don't forget to encapsulate the two quantities you're separating in parentheses. Okay, so this parenthesis here will prevent me from making sign errors, so this is really, really important. So if I plug in 3, I have 3 squared over 2 minus 3. Okay, so from here on out is just arithmetic. Okay, so what do we have? 2 times 3 is 6. 6 minus 2 times, using order of operations here, we have 5 squared is 25 over 2 minus, since we have a fraction here, I might as well just express 5 as a fraction with a denominator of 2. So put this over 1, times it by 2 top and bottom, you have 10 over 2, just to save time. Because if you look at the second quantity here, we have a 2 at the bottom there too, so we might as well. 3 squared is 9 over 2 minus, how about we express 3 as a number with a common denominator, an equivalent fraction with a denominator of 2, so 6 over 2. Bam. Alrighty, now we have 4. Let's express 4 as well, let's just write a 4 for now. 4 plus, and then here we have 25 minus 10, which is just 15 over 2 minus 9 minus 6 is 3 over 2. So we have 4. We can write 4 as what? 8 over 2. So 8 over 2 plus 15 over 2 minus 3 over 2. So 8 plus 15 minus 3. 8 plus 15 is 23 minus 3 is 20 over 2. And your final answer is 10. Okay. Answer to number 13 is option letter D. Okay, let's take a look at question number 14. It says if f of x equals the square root of x squared minus 4 and g of x equals 3x minus 2, then the derivative of f of g of x at x equals 3 is... now, one thing you want to recall concerning differentiating composite functions, okay? A function inside a function like f of g, that's a composite function. If you're differentiating composite functions, you use the chain rule, okay? Alright, so we're going to be using the chain rule here. Let's go ahead and set it up first. So let's say we want to find derivative of f composed with g of x. Okay, so we have this composite function here, and we want to find the derivative. So we're going to use the outside inside rule or the chain rule. So it's going to be the derivative of the outer function evaluated at the inner, okay, multiplied by the derivative of the inner function. So you differentiate in layers. You never differentiate two functions simultaneously. You do one first, evaluate it at the inner, and then you multiply by the derivative of the inner. Alrighty, so this is what we're going to use for this problem. Okay, let's go ahead and set it up. F of x equals the square root of x squared minus 4, and g of x equals 3x minus 2. Okay, I don't need to compose them before I differentiate. I can just apply the chain rule directly here as I'm about to do. So check this out. The derivative f prime of x, this in and of itself is a composite function. So if I differentiate this, I'll have 1 over 2 root x squared minus 4. But it's a composite function. I have to differentiate the inner, which is times 2x. Okay, and then g prime of x, we differentiate that. Derivative of 3x is just 3, and derivative of 2 is 0. Alright, so what we're going to do is, this is the derivative of the outer, so we evaluate it at the inner. So that basically means we're going to take g of x and plug it into f prime. So all the x's in f prime will take on the value 3x minus 2. So that's this portion here, f prime of x, f prime evaluated at g prime of x, and then we'll just multiply it by the derivative of the inner function. Okay, so let's do the first part. Notice these two 2's can divide out. Okay, so we can just take those 2 out while we're at it. So the derivative f prime of g of x multiplied by g prime of x is equal to, so instead of x, we're going to put in g in there, so we have 3x minus 2, and then we have that divided by, in the bottom we have a square root of, so instead of the square root of x squared minus 4, you take the x out and put in 3x minus 2. 3x minus 2 square minus 4. So this right here is f prime evaluated at g. Okay, the derivative of the outer function evaluated at the inner function. So multiply this by the derivative of the inner function, which is just 3. Alrighty? Okay, so this is the derivative. Now, to finish it off, we just have to evaluate the derivative at 3, right? So f of g of 3 prime is just this function we got, f prime evaluated at g of instead of x3 times g prime of 3. What does that mean? Just plug in 3 for all the x's. Okay. Alright, so if I plug in 3 here, I have 3 times 3 minus 2. And then that divided by have a square root divided by the square root of quantity 3 times 3 minus 2 square minus 4. Okay, and then we also have another 3 right here. We don't want to forget that. Alright, so what do we have? 3 times 3 is 9, so we have 9 minus 2 multiplied by 3. And then we're going to divide that by still have the square root there. Square root of 3 times 3 is 9 minus 7. So 7 square minus 4. So 9 minus 3 is 7 times 3 is 21 over 7 squared is 49 minus 4 is 45. Okay, so we have to simplify this. So root 45, we can break this down whichever way you want to do it. So it can take out 3 goes into 45 15, 3 goes into 15 5 times. So these two 3's break out as a 3. Okay, so root 45 is 3 rad 5. That's one way of doing it. You can also do this as root 9 root 5, which is equal to 3 root 5. Whichever method works for you, okay? Alright, so this becomes 21 divided by 3 root 5. And then we can simplify further. 3 goes here once, 3 goes here 7 times. And your final answer is 7 over root 5. Okay? And that is option letter A. Okay, let's take a look at question number 15. Okay, it says the graph of a differentiable function f is shown above. If h of x equals the integral from 0 to x of f of t dt, which of the following is true? Alright, so one thing you want to remember concerning the connection between the sign of f prime and the behavior of f is that if f is positive on an interval, then if f prime is positive, then f is going to be increasing. Okay? And if f prime is negative, of course, f is going to be decreasing on that interval. Okay, so we know what h of x is. H of x is the integral from 0 to x of f of t dt. When you see something like this, the hint or something you want to call to mind is that we are going to be using or might be using FTC part 2 for this problem. Okay, because you have a functional limit of integration in f of t dt. Okay, so we're looking at all 6's here. If you look at all the options, we're looking at what is happening around x equals 6. Let's start by looking at h of 6. What is h of 6? For h of 6, you simply input 6 into the function and see if we can quantify what the result will be. The integral from 0 to 6 of f of t dt is the area here, this area, the accumulated area from 0 to 6. Since the function is below the x-axis on that interval, what does that tell us about the area? The area is going to be is going to have a negative result. Okay, because it's underneath. The area is going to be negative. So we know for a certainty that this value will be less than 0. Okay? Now how about h prime of 6? H prime of 6 is basically we have to find the derivative of this function, and then we're going to evaluate it at x equals 6. So anytime you're evaluating a derivative at a point, always recall that there are two portions to it. Okay? Alright, so for h prime of 6, first of all, let's look for h prime of x. H prime of x is going to be the derivative of this integral, 0 to x of f of t dt. So using FTC2, as I indicated earlier, we're just going to take the upper limit and plug it into the function and multiply it by the derivative of the upper limit. We're not going to bother with the lower limit because when we plug in 0 and times the derivative of 0 is just 0, that whole thing will become 0. Okay, so we're going to have f of x times 1, which is just f of x. Okay, so that's what the derivative is. Now the second part, we're now going to evaluate the derivative at x equals 6. Okay, so h prime of 6 is simply going to be f of 6, since h prime of x is f of x. So f of 6 is simply the output value of this function f of x when x is equal to 6. So what's the output? The output value is 0. Okay, so f of 6 is 0. Alrighty, now what's last? If you look at the options, we are comparing h prime, and h double prime. Okay, so let's take a look at h double prime of 6. H double prime of 6 is going to be f prime of 6. Okay, so h double prime of 6 is going to be f prime of 6. Now how on earth did I know that h double prime of 6 is going to be f prime of 6? Well, let's take a look at the previous work we just did. We found out that what did we find out? We found out that what is it? H prime of x is f of x, right? H prime of x is f of x. So what do you think h double prime of x is going to be? H double prime of x is going to be f prime of x. Okay, and then h double prime of x is going to be, h double prime of 6 is going to be f prime of 6. So that's how I was able to arrive at this conclusion, because I looked at the previous connection right here and I saw that h prime is f of x. So h double will be f prime of x, and then h double prime at 6 will be f prime at 6. Okay? Alright, so what's the sign of the derivative of f at 6? What is the behavior that will tell us what the sign is? F is increasing. F is increasing at 6. You see it is going up, 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 up. So if f is increasing, what does that tell us about the derivative? If a function is increasing, the tangent line is going to be going up from left to right. So let me just sketch in the tangent line for you there. So the tangent line is going to look something like this. So since the function is increasing, the tangent line is going to be going up, which means it is going to be positive. Okay? Remember we talked about it earlier that if f prime is positive, then the function is going to be increasing, right? So we have an increasing function that tells us that the derivative is going to be positive. So f prime of 6 is going to be greater than 0 since f is increasing at x equals 6. So if a function is increasing at a value, then and it's differentiable at that value, then the derivative is going to be positive. Okay? Alright, so can we order these? Absolutely. H prime of x is negative. This one is negative. H of 6 is negative. H prime of 6 is 0. And H double is positive. So this is the smallest one, followed by this, and then the biggest is H double prime of 6. Alright, so let's order it. So our answer is going to be H of 6 is the smallest, is less than H prime and H double. But we know H prime is less than H double, so followed by H prime, and that's less than H double prime of 6. Answer to number 15 is option letter A. Thanks so much for taking the time to watch this presentation. I really appreciate it. If you found the contents of this presentation helpful in your preparation for the upcoming AP exam, you can support us by giving us a thumbs up or sharing this video with your friends. If you have any questions or comments about the contents of this presentation or any AP Calc question in general, just place your questions in the comment section below, and we'll be more than glad to support you. Don't forget to subscribe to our channel for updates to other AP Calc prep materials such as this. More clips can be found on mathgotserved.com. Thanks again for watching and have a wonderful day. Goodbye.